Let's talk in a little bit more detail about the sizes of fundamental types. Now, I certainly understand that it can be a little confusing when you're approaching the language for the first time to deal with the fact that fundamental type sizes can vary from implementation to implementation. So I wanted to spend a little bit extra time here just going back over some of the things that we've talked about in our discussions of the different fundamental types in C++ and look at their sizes, and hopefully we can come away with kind of a little bit of a rule of thumb in terms of how we can think about these things. So as I said, the sizes of fundamental types in C++ are implementation defined. In other words, they can vary across different compilers. And although that's actually a potential source, as I said, of some confusion when you're first learning C++, proponents of the language actually view it as a strength. For one thing, it allows you to program with an eye towards the hardware characteristics of the platform that you're programming on. There can be significant differences from platform to platform in terms of memory access times, computation speed, and so on. And C++ therefore allows you to choose the appropriate fundamental type for a given variable to try to achieve the highest performance you can get, provided, of course, that you're well acquainted with the hardware itself. Now, whether you're interested in trying to squeeze that last ounce of performance out of your machine or not, it's still important to understand the possible differences in size between, say, the different versions of an int or the different floating point types. For the most part, the C++ standard does not dictate particular sizes for particular fundamental types. It does, however, enforce a relative ordering among them that I think can be helpful when we try to think about these things. So let's look at the sizes of the integer type. You can line them up basically from left to right, going from smallest to largest, in other words, from narrowest storage space to widest. And we'd have there the char, then the short, then the int, then the long, then the long. So we're just kind of lining them up again from left to right, at least in terms of their potential storage capacity. And one way that it might help to remember the different possibilities for the sizes of these things is just to go kind of from left to right, but looking back at the previous value each time. So a short, for example, has to be at least as wide as a char. An int has to be at least as wide as a short. A long has to be at least as wide as an int. And finally, a long has to be at least as wide as a long. Now, if you look at this for a second, you realize that this means, again, maybe somewhat confusingly at first, that it's entirely possible for you to have two different integer types that are the same size. And for example, on a lot of systems, an int is actually the same size as a long. It can be 4 bytes wide very often. And with regard to the floating point types, we can do the same thing. We can line them up basically from left to right in terms of potential sizes, so float, then double, then long double. And we can remember that a double has to be at least as wide as a float, and a long double has to be at least as wide as a double. Now, what if we were interested in checking out the sizes of these data types on our actual system? Well, let's take a look. I've written a program here. I didn't want to bore you by having you sit here and watch me type it out, because a lot of these concepts are things that I'm really just trying to demonstrate to you in this initial phase of us kind of getting up and running with the fundamental types of the language. And I'll supply this source code on the Canvas site so that you can have it available. If you just want to download it and run it on your machine, it will help you see what the widths are of the data types on your computer. Some of this actually will already be familiar to us, though, right? We've talked very briefly in previous lessons, including our Hello World demonstration, about, of course, the main function. We talked briefly about this using directive. We'll talk about it in the near future as well, this preprocessor directive as well. But for now, we're just focused on the contents of our main method here. Here I've declared a char called mychar. Again, not super creative variable names, I'll grant you that. A short called myshort, and so on. So basically, I've just tried to declare each one of these possible fundamental types so that we can see the various sizes. In C++, now there's a little bit of subtlety here, but we can use the size of operator as a practical matter to tell us the number of bytes that a particular data type, fundamental data type, stores for us. So here I've got a cout statement that just basically prints out mychar and then a couple of tab. These are going to be interpreted as tab characters, right? You've seen that before in Java, for example. And then we use this size of operator, and we pass mychar into it, and that's going to give us the number, in this case, the number of bytes that mychar occupies on this system, on my computer specifically here, because I'm running this on my machine. We're going to do the same thing with short and int and long and so on all the way through. And then we'll just be able to print out and see what these data types are stored in terms of their storage space, the number of bytes that they're stored in on my system. And then you can run this code if you want to. If you're curious about this, you can run this code on your machine and see if you get the same results. So if I just run that, I'll just hit Control F5 there. Let me zoom in. We can see that on my system here, a char is 1 byte, a short is 2 bytes, an int is 4 bytes, and then this is kind of what I said during the slides. This can be a little surprising maybe sometimes the first time you see this. A long is actually the same size on my system as an int. They're both 4 bytes wide. And that is true to that requirement that a long has to be at least as long as an int, right? And that's the case here. It doesn't say it has to be longer than an int. It has to be at least as long as an int. And then a long on my system is 8 bytes wide. You can see that a float is 4, a double is 8, and again, we have that same sort of issue here, right? A long double just has to be at least as long as a double, and that's true in this case. They're both 8 bytes wide. So this can be a useful exercise just to run this program on your system and kind of have that reinforced for yourself, this notion that even though we have this ascending order of widths, it's not strictly greater than. Sometimes you can have adjacent data types that have the same width. Okay, so here we've taken a look at the sizes of the fundamental types just to help us clear up any confusion there, and thanks very much.